this wonderful meeting. So today we have two talks lined up. Our first speaker is Sumedha from NICER, and she'll tell us about random field spin models. So Sumedha.
Point.
Forward slide. This is backward laser.
Yes. So good morning all. And it has been a very nice conference till now. I thank Sanjeev for the invitation, and best of luck, RRI. It has been a great institution, and I hope it continues to be the same. So today I'm going to talk on, I think, a topic which is not being covered a lot in this conference, and which is a very old problem in physics, which is the problem of many body spin models in the presence of random magnetic quenched field. So, you can have many kinds of fields, but typically when we say random field spin models, we are most of the time talking of the magnetic spin models. So, I'm Sumedha, and I've been working for last quite a few years at an institute called National Institute of Science Education and Research, which is located in a city, Bhubaneswar, which is on the east coast of India. It's a very beautiful place. And like some other people had this obligation, some of us are DAE institutions, Department of Atomic Energy institutions, and we are supposed to say that we are also affiliated to Homi Bhabha National Institute, which is the degree granting body for all these institutions. Okay, so the work I'm going to present is a work which is a combination of work done with Santanu Das, who was a postdoc till recently with me, Soheli Mukherjee, who was a PhD student who finished last year, and Mustansir Burma, who is in the audience. And it's especially nice that the work I'm going to present involves the work of Santanu, because he was a PhD student with Sanjeev at RRI, and then he came to NICER. We had some very good productive time, and now he has hopefully been able to move to Hebrew in Bar-Ilan, because he was going to go in October. Okay, and so he was a PhD student with me, who is also a postdoc right now in Israel at Ben Gurion University with Naftali Smith. Okay, so I thought since it is slightly different, so just for the sake of pedagogy, let me just start with the simplest kind of random field model, just to say why these problems are interesting and what is non-trivial about them. So this is a very simple Hamiltonian. The first term is the ferromagnetic term. In this case, it's a pure ferromagnetic interaction. And in the second term, we have a field which depends on the sides, which in this case is a quenched field picked from a distribution. So one can see that there is a competition between these two terms, which I have just shown here as from a cartoon. So these red arrows you can take as the arrows. Strictly speaking, if S is scalar, these are not arrows. But if you think of vector spins, then something like that you can think. Otherwise, there are just two directions for the field. So red arrows are the directions of the field at every side, and blue arrows represents the spins. So if the first term dominates, the spins will try to align, like in this first figure. Okay, and there will be a cause, because the second term will not be happy. And there is another scenario where the spins might choose to align with the fields, but then the coupling term won't be happy. So there is a competition in this, besides what happens when you put a temperature, between the fact that the spins want to align themselves and there is a random field destabilizing it. The problem has a very long history, and there are issues related to which dimension we are talking about and stuff like that. But I will focus today mostly to results in the mean field limit or on fully connected graph, and I'll not mention anything about what happens in finite dimensions, which is very significant. I will be happy to say something if there is some, if people want to ask, but I don't know too much there, but I know some things. Okay. So I will, the history of the problem is also very old. So these two are perhaps two of the oldest papers where the problem was solved in the mean field limit or on a fully connected graph by Snyder and Piet, and then Arani extended this work, And this was using the replica trick. And one of the interesting things and the surprising things at that time was the fact that if you know, H0 is the strength of the disorder field. So if you take your HI, the disorder, from a Gaussian distribution and look at the system for phase transitions, the phase transition here is the usual transition between a magnetic state, a ferromagnetic state and a paramagnetic state. Then in the TH plane, there was a line of continuous transitions. The solid line here represents a line of continuous transition between the ferromagnetic phase here, I should have written that, and the paramagnetic phase outside. But on the other hand, if you take the HIs from a bimodal distribution, it was found that the phase transition changes, which was kind of strange. You know, we don't want the behavior of the system to be too dependent on the details, but that's what was found. And it was found that if you look at the temperature versus the strength of disorder field phase diagram, there's a solid line here which represents a line of continuous transitions, and there's a dotted line here which represents a line of first order transition. And this is a nomenclature I'll have throughout my talk. Solid line will be a continuous transition, dotted line will be a first order transition. And these two lines meet at a point which was called TCP, or the tricritical point. Okay? And what was special about this point? If you look at this continuous line, this is like what is a lambda line for another kind of a model. The universality of this line is the same for every point on this line falls in the same universality class, namely the Ising universality class. Whereas if you are at the TCP, it's a different universality class, sometimes which is also known as the tricritical universality class. Okay, both these distributions are symmetric distributions, and so this was one of the things which was interesting at that time. And also in this paper, RNE also made another conjecture, which also I plan to touch in my talk, where he conjectured that the phase transition at low temperature will be first order if the random field distribution has a minimum at 0 field, and it will be second order if it is maximum at 0 field. So we'll see.
Similar for the bimodal distribution, H naught is, so it's centered at minus H naught and plus H naught, or what is
Yes. So I will show the distributions. You know, I didn't add it to the introductory slide. Yeah.
So this is for the fully connected
Yes.
problem, right? And
Yeah.
in that case, you don't need to scale J with system size, is it? Like J by N or something?
So, you know, the Hamiltonian, I'll show you the Hamiltonian for the fully connected graph. So I should have written the Hamiltonian carefully, but you know, yeah. So I should have had an N here if I'm saying it's for the fully connected graph.
Okay.
But you know, this, that part will come. Okay. This is just as an introduction to tell you what the diagrams are. So there's a lot of motivation to study these models. So, so I will not go into all these motivations, and you know, maybe there are more, but this is just to say that it's a very important problem, and perhaps it will continue to be a very important problem. So here's the outline of my talk. I'll talk about the random magnetic field disorder in 3 cases. The first case is the Ising model, but we will look at asymmetric distributions. There's something interesting which happens there, which helps us understand what happens for the random magnetic field in the case of Bloom-Kapel model. The Bloom-Kapel model is a model where there are 3 states in the system. Okay, and then I will also hopefully get time also to talk about what happens with the random magnetic field disorder when we take continuous spins, for example, the XY model. Okay, and you know, there can be disorders of other kinds, and this is just maybe me being greedy about saying something about it. There's another kind of disorder, the crystal field disorder. If the time is still left, maybe I'll flash some results for this model. Okay, so you know, random field Ising model, and as I said, we are just talking a fully connected graph. But the new thing, and strangely, which has not been looked at so much, is what happens when the distribution is asymmetric. Okay, it wouldn't have been so interesting if not much was happening, but we find that asymmetry has a drastic effect on the behavior of the system. So now, Sanjeev, there's N. So this is the Hamiltonian on a fully connected graph for the random field Ising model, and this is the distribution QHI from which we are taking the random fields HI. So as somebody said, it is peaked at plus H0 and minus H0, and R can take values between 0 and 1. If R is half, then we have the usual symmetric bimodal distribution. And I'm going to consider both. One, that when the Ising spin takes 2 values plus minus 1, and when the spin SI takes 3 values 0 plus minus 1. Okay, but note that at this stage, besides 0 being diluting the system to some extent, these two are not really two different models, and that we can see even here. Again, I am showing you the same phase diagram which I had 2 slides back. It's a phase diagram between the temperature and the strength of the disorder field H0, and in the spin half case, you can see the solid line is the continuous line of transition, dotted line is the first order line of transition. They meet at a TCP, and the same thing happens when I have a 3-state system. The reason I am showing this for the 3-state system is because when we add a crystal field, things are going to change, and this is like a reference when we are talking of the system with the crystal field. Now, what happens if R is not half? If I make R to be say 0.55, this is where it was surprising. And in fact, when we submitted the paper also, the referee said he or she redid the calculation because they were also little taken back by this, that what one finds is that this line of continuous transition actually just goes away. There's no more a line of continuous transition. There are lines of first order transitions, and they are ending at a point which looks critical, and this point we call it as an ordered critical point because it is not a usual critical point between between an ordered and a disordered state. It's a point between 2 ordered states. Okay, and this plot is not very important. It is just showing how this ordered critical point location changes as we change the value of R. Yes.
From which phase to which phase are the transitions?
So ordered phase, a critical point you're asking?
No, when you break the symmetry in the...
Okay, so let me say it. So in this case, as I said, this one is a ferromagnetic phase, and outside the line is a paramagnetic phase. Okay, now here, both the phases in some sense are ferromagnetic. Okay, so I will show you that. Okay, so coming to Rajesh's question, now so how do I know if it's a critical point? Now I cannot do a simple continuous Landau expansion, but obviously we can do something else. So okay, I'll again show how one gets this free energy functional for this model in later slides when I'm talking of 3-state system, but I have here just quoted what the free energy functional is. The free energy F of the system is the minima of this function. C is 0 when spin is half, and C is 1 when spin is 1. Okay, we heard a lot about free energy functionals from Pradeep yesterday. So to find the OCP, we just have to take the first 3 derivatives of F tilde M and equate them to 0, making sure that the 4th derivative is greater than 0, and the point where they meet would be a candidate for a critical point, and that then we can check by actually looking at the magnetization and the magnetic susceptibility. So you can see here, this is how the magnetization look near that red dot. It goes from low temperature 1 to something and changes its slope here. So it is not 0 at the ordered critical point, it is some finite value. And if you look at the susceptibility, you can actually see that the susceptibility indeed diverges at this point. Okay. Sorry. So the axis is temperature. So you can see here the axis has been zoomed to just show the divergence. Yeah. Thank you. Okay, so that is one thing, that the phase diagram and the OCP for the problem. There is something more we saw. So I showed you one plot for magnetization around this point, but in regions near this, Santanu noticed something else. Okay, one more proof of how OCP is different than TCP. So we checked the scaling of the magnetization with respect to T. So one can see when it is symmetric, the exponent is 0.25 or 1 by 4, which is the exponent for the tricritical point, and when the distribution is asymmetric, the exponent is 0.5. So from this one can see the nature of a TCP and OCP is different. Okay, so besides this, there was something else which seemed kind of little interesting, and what happened was very close to this OCP, only when R was not equal to half. If you look at the first 3 plots, these are the plots of magnetization as a function of temperature, and there seemed to be a non-monotonic behavior in the magnetization. Okay, there's no transition, but as the temperature is increasing, there seems to be a region where the magnetization is increasing. Okay, so this is basically what we learned by looking at the asymmetric distributions for the random field Ising model. I didn't show you what happens for the asymmetric Gaussian distribution, but we checked it, and in that case, there's just no transition. The magnetization just continuously changes as you change the temperature. Okay, and actually, we found 1 or 2 studies of the asymmetric random field Ising model, and there also they had shown that any infinitesimal asymmetry in the distribution is going to change the nature, and especially if there was a TCP in the system, it will change to to a critical endpoint. But if there is a critical endpoint, that means there must still be some amount of continuous transition hanging around. But it turns out that we find that the universality class of critical endpoint and the ordered critical point is the same. It should actually be a ordered critical point, and maybe it has some relevance for experiments with porous media, because there one considers that random field Ising model is a good realization, but then there's some problems with matching the exponents with the random field Ising model, because most of the time people are matching it with the exponents for the symmetric distributions. Okay, so this is the story for spin half. Yes. Okay, if you do the simulations, and then for the finite amount of disorder averaging, there's no self-averaging. That's why simulations are hard for this system. But I'll show you the free energy. It's the free energy from doing the quenched disorder averaging. So it is exact. But simulations, self-averaging is a problem. That's why it continues to be a very hard problem in simulations. Okay, so now I come to the 3-state model, where there is something more interesting that we saw. And before I come to the disorder case, I thought, I'll just introduce the pure model where there's no disorder, and it is known as a Bloom-Kipple model. So now the spins are +1, -1, and 0. In this case, you can change the density of +-1 versus 0 spins. So one can add a term which is like a crystal field term, which is like delta summation SI square, and the phase diagram for the pure case in any finite dimensions and mean field qualitatively is the same. It has 2 order parameters, the average value of S and the average value of S square, M and Q respectively, which I am calling. And if you look at the phase diagram in the T delta plane, it is similar to what I showed you before, but it's a completely different model. There is a line of continuous transitions, there is a tricritical point, and there is a first order line of transitions. So this model is a very old model given in 1966 and this was given basically to explain the first order ferromagnetic transitions in the absence of magnetic field, which was seen in some materials like QO2 and all. Okay, and since tricritical point, I've been talking a lot about it, and there were a few other talks also of tricritical point. So I thought I'll also show you why it's called. People know, but just for the sake of completion, it is called a tricritical point because, for example, if I now add external field and draw the phase diagram in the 3D space, then there are 2 other lines of transition which meet this point at this dot. Okay, the lambda plus and the lambda minus, these are also lines of continuous transitions which are coming from the H plane, and since 3 lines meet here and all 3 are lines of critical points, it's a tricritical point. And In fact, there's a recent work which has rigorously shown that, TCP exists in all dimensions greater than or equal to 2, though perhaps we didn't need that confirmation. This is just, I will just quickly flash that, this kind of phase diagrams are actually seen in the systems. Okay, so now I will, I didn't show it the calculation for the icing case. I'm going to show it taking the example of the spin one, how we do these calculations. We do these calculations using the large deviation principle, and the way we do it is, for example, this is the Hamiltonian for the infinite range spin one model, and these both terms need not be present at the same time. In fact, somebody told me that practically from materials point of view, it's impractical to consider both together, but that's a different issue. But the point is, there's one interaction term, and there can be field terms with quench field, which can come in various kinds, like the HISI or delta ISI square. Doesn't matter which kind it is. The important thing is the disorder is in the field. Okay, so then if there's a configuration Cn with these two order parameters x1 and x2, and one, then one can say that the probability that a given configuration has values x1 and x2 satisfies the large deviation principle, with I being the rate function for this problem. So the way to solve it, and this is the only slide to just quickly say what it does is, first you find the rate function corresponding to the P I showed before, but when the interactions are switched off, I call that Rx1, x2, and then it turns out that if this Rx1, x2 is a rate function corresponding to PHNI beta, if there is a probability function PH beta which is connected to PHNI beta via form like this, then the rate function for PH beta, the I, will have a form like this, and this comes from a tilted large deviation principle. And on a fully connected graph, we are in a good state because we can write the interaction term in this form. Okay, so that is why we can use that and actually get the exact form of I, and this I is actually like the free energy functional for the problem, and this whole process involves a lot of saddle points, and then you look at the other more saddle points of this function to find the phase diagram of the system. So for example, this is not related to anything I'm saying, but it just shows this function I near a continuous transition in the first two diagrams. You can see when it is in a paramagnetic state, it is just like what you might have seen for the Landau functional, and when there's a continuous transition, that minima splits continuously into two symmetric minimas. When there is a first order transition, you can see that here the zero state is preferred, and this is a second minima which is not the global minima, but the moment the system shifts, that becomes the minima. So this function works very well like a free energy functional, something which I think Trideep also talked a lot in the context of non-equilibrium systems. Okay, so now I come to the random field Bloom-Capel model. So it's again, there's a magnetic field disorder here, but now there's a difference. Spins are plus minus 1 0 spin. It's a 3-state system, and there is a crystal field here. So before I go to what happens when the field is asymmetric, let me tell you what are the results when we take a symmetric bimodal distribution. In this case, this is how the free energy functional looks, and from this free energy functional, we can take the limit beta going to 0 to write the ground state free energy of the system, from which we can obtain the ground state phase diagram also. Already the ground state phase diagram in this case is quite interesting. It has 4 phases. F is the usual ferromagnetic case. This is at 0 temperature, so F and Q are 1. You can have a paramagnetic phase with M being 0 and Q being 1 minus P. And you can have a F1 phase which is magnetic but not fully magnetic like F, and you can have a non-magnetic phase where you basically have all spins to be 0. Okay, so now this is the 0 temperature phase diagram of this model when we have symmetric bimodal distribution. Now if we look at the finite T, either we can fix delta or we can fix the strength of the external field. Okay, so depending on, here I am showing you the phase diagrams where we have fixed the value of delta, and then depending on the range of delta we are looking at, the nature of the phase diagram changes. And I have shown you these are the 6 phase diagrams which show up. So again, the solid lines are the lines of continuous transitions, and the dotted lines are the lines of first order transitions, and there are many different kinds of multi-critical points show up. This circle is the usual tricritical point. Star is what is known as a bicritical point. I will not talk about this today because I will not talk about the phase diagrams in the presence of external field, but basically this is a point where your lambda line is gone, but the 2 lines which were coming from the external field side, the continuous lines, they're still there and they meet at the BEP. And A5 here is a point of 5-state coexistence. So these are the phase diagrams, and these phase diagrams, I've given the main references, but there might be some other papers also where some parts of these phase diagrams have been shown. But the main objective for me to show this phase diagram is to contrast it with what happens when there is a asymmetry in the distribution. So now again we have the distribution, and the R here is no longer half. For example, here R is 0.55, the same value for which I had shown the random field Ising model with spin 1. So that was like delta equals 0. And now we increase delta. So here magnetization is plotted as a function of temperature. So purple plot is for delta being 0.2. So we see it is non-monotonic. But if you increase delta further, it looks like this green line, and this red point actually, I'll show you later, or you can see here in the inset, at this point the magnetic susceptibility is diverging, is a ordered critical point. And turns out if I increase delta further, if we increase delta further, then this becomes actually a transition, a first order transition as the temperature increases from a low ordered state to a large ordered state. So when I have a 3-state spin system and there's an asymmetry in the distribution, one actually finds that there can be an inverse transition in the problem. Okay, so this is what we found for this problem. And not just this, then Santanu was, did a very careful study of all the parameters, and he even found that there is a range of parameters where the magnetization can undergo 2 first order jumps. First, it jumps to a higher value, the inverse transition, and then it comes back to a usual value as the temperature is further increased. This was interesting because many of the systems where people had reported a first order inverse transition, they had talked of sometimes also of a second first order transition happening again from a order to a less ordered state. Okay, so what about the entropy of these different transitions? So here in the on the right, you can see I have plotted magnetization. The green curve is along, when one is sitting at the near the OCP, what happens? Okay, and the purple and the blue curve is when there's only one first order transition and then it slowly decays the magnetization, and purple is for the case when there are 2 first order transitions. So you can correspondingly see that entropy is as expected. The entropy in the green case is a continuous line, okay, and the entropy in the case where there was a first order jump has 1 first order jump clearly seen, and in the case there are 2 first order jumps, again you can see both of them are entropy increasing transitions. In both cases there is a first order jump in the entropy. So indeed there are 2 jumps, and one of them is an inverse transition. Now then obviously, so what is the full phase diagram of the model? So again I am showing you the phase diagram as one fixes delta and plots T versus H phase diagrams, and again one finds there are no continuous lines in the transition in the phase diagrams. For example, when I had shown the phase diagrams for the symmetric case, there were all kinds of continuous lines, but in this case there are no lines of continuous transition. What is there are only the lines of first order transitions and these red points which are like the ordered critical points. So one uses the same way to locate them, and there is a color coding of these first order lines. So black is the usual first order line of first order transitions, which are the usual first order transitions. Blue here is a line of first order transitions, which are inverse transitions in N. The magnetization along this shows a first order jump with the inverse transition. On the other hand, the greens are the lines where there is an inverse transition happening, but happening in Q. Okay, so this is the phase diagram we obtain for this model, where the phase diagram are simpler than the symmetric case, and they only have first order lines of transitions and ordered critical points. Now, to understand them, one can take these ordered critical points and map them or put them on the ground state phase diagram. So this is the ground state phase diagram. The nature of the ground state phase diagram for any R is not different. What is different is the slope of the lines in the phase diagram. This is the zero temperature phase diagram, and these red lines are the lines of projections of ordered critical points as seen at whatever values on this phase diagram. So they seem very close to the first order transition lines in the ground state. So so that kind of tells us what is happening when we have a symmetry in the transition. Basically, there was a zero order transition which stayed for some time before going away. And another way to look at it is that the same phase diagram, if you zoom around these regions, you find that there is a green region of the parameter values of delta and H0. If one starts with those values, then one sees a inverse transition, but one sees an inverse transition if one starts with one of these values. So there is a way to understand it, and crucially it depends on the fact that F2 and F3 states have the same entropy in this case. If one plots these, the coordinates of the multi-critical points for the symmetric transition, then also it might look similar, but the area, the green area goes to 0. And indeed, in the case of the symmetric transition here also, there was no inverse transition in the problem. So conclude this part. Asymmetry in the disordered distribution destroys the lines of continuous transition. Asymmetry in the disordered distribution gives rise to inverse transition, and the location of inverse transitions can be inferred from the ground state phase diagram of the model. Okay. So I changed the chronology to say, it's not that actually spin 1 models have been candidates for inverse transitions. I think it started with the paper of Schupper and Schnell in 2004, where they artificially kind of changed the entropy contribution when there is a spin +-1 or there is a spin 0, and that helped them to get an inverse transition. And there is a series of papers, a lot of them actually, by Luca Leuzzi and others, where again they link it, the inverse transition with the glassy systems with glassy phases, basically the systems with random bond interaction. In fact, there was a feeling that if you add random field, it is going to suppress the inverse transitions. So what is different here is there is no glassy phase, we just have random fields, but there are inverse transitions. And inverse transitions are also seen in experiments involving solutions which are good candidate models for spin 1 Bloom-Kipple like models, or in vortex lattices. So these are some of the references where there have been inverse transitions have been reported. Another interesting reference in this case is that there was actually one more paper, I should have cited that also, which came in 2017. If people took the pure Bloom-Kipple model, but took the heterogeneous degree distribution on a random graph, there was an inverse transition. But now one can understand that transition also from what I showed, because in that case, if you try to write a mean field, because of the heterogeneity of the degree, one will produce heterogeneous fields at each site. Okay, so in some sense, it is kind of understandable that the topology can induce these phase transitions also in these spin 1 models. Okay. Yeah, so that was about the asymmetric transitions. How much time? 10 minutes. Okay, so I'll go through these slides quickly. So this is just to say that is the main part of my talk. But we have also looked at more symmetric distributions, and we are also looking at the corresponding asymmetric distributions right now. So Sohaili in her PhD actually also studied a trimodal distribution and a Gaussian distribution, and one of our motivations was to check Hermite's conjecture, because that was for the ON model, and we are dealing with spin 1 models. So there's no reason it should hold or it does not hold, one doesn't know. So the life gets very complicated. So depending on this P is actually the R which I have been saying, but on this slide, okay, I made it P, okay, because in that paper we used P. So then depending on the value of P, one can have very different kind of phase diagrams. One thing, the P equals 0 is the symmetric bimodal case. The new thing that happens here at the ground state level is that there is one more extra ferromagnetic phase. Okay, so now there are 3 ferromagnetic phases in the ground phase. And when you try to study the phase diagrams, she actually worked very hard on this, and depending on which range of P you are, the class of phase transitions can happen, either fixing delta or H, and these are all those phase diagrams. But you can see there are continuous lines, there are first order lines, and there are all kinds of multi-critical points. Not necessarily we understand each of them, but it's a fact that the phase diagrams are very rich and very sensitive to the disorder distribution. The other thing that she studied was the Gaussian distribution, symmetric Gaussian distribution for the random field spin 1 models. Somehow that had not been studied. And this is the 0 temperature phase diagram. Sigma is the variance of the Gaussian field. And this diagram kind of looks similar to the pure Bloom-Kipple model. In fact, one can say sigma is like the temperature, another temperature in the model. Okay, but when you look at the finite temperature, and these different plots are for different values of delta, one finds that at large enough deltas, actually even at low temperatures, one doesn't have first order transition. So the transition, even though the disorder is Gaussian, can become continuous in this case. Okay, so this was another of the results that we had about the spin 1 models. Recently, she has looked at the asymmetric Gaussian distributions, and she again finds that the continuous lines of transitions are going away the moment the disorder distribution is asymmetric. So these are 2 discrete spin models. So I will quickly, maybe in 3 leftover time, talk about another system where we have studied the effect of random magnetic fields, and it is the random field XY model. So this is again a very well studied model, but we used along with Mustansir, we studied it using the large deviations, and this is what the large deviation function looks like. I here is the modified Bessel function, and from this, if you look at the phase diagrams, so these are the 2 phase diagrams for this model, both for symmetric distributions, uniform and the symmetric cubic distributions. In both cases, there's a line of continuous transitions, there's a line of first order transition which meet at a TCP. We could say a few things more generally about these phase diagrams, one of them being that it turns out the equation of line of continuous transitions is the same, as long if the distribution of the angles, the distribution from which the quenched angles have been taken, satisfy this property, which Mustansir said is like quadriperiodic property of the distribution. And there were few other aligned features of these calculations, like though the line of continuous transition was the same, but the location of TCP, the tricritical point, depended on the distribution, and the line of the first order distribution was also dependent on the disorder, but not very strongly. So this slide I will skip, and to show that last point, for example, if I am at the 0 temperature, the ground state of the system can be given by this energy. Then in the uniform case, the energy comes out to be this, where E is the elliptic function, and at 0 temperature, there is a first order transition at some value of Hc, which in the cubic case is slightly different. So this is the main difference when one took two different symmetric distributions. Another thing one could verify by looking at this was the fact that if the specific heat, the specific heat went to constant as T went to 0, which was kind of expected because one would expect some kind of low-lying excitations in the system. Okay, so yeah. Okay, so I think I'll end my talk here, and I realized that I don't have a conclusion slide because that conclusion has some conclusions from here as well. Yeah.
Yeah, so we can have questions.
Maybe there is something I didn't understand. I thought the specific heat for the random XY model, as temperature goes to 0, it seems it didn't go to 0.
No, it went to a constant.
So it breaks the third law.
Yeah.
So,
Okay.
is there like a residual entropy that
Sorry, I couldn't get the question.
the specific heat in many cases?
Yes, so there is some entropy, yes,
and
because of the random fields.
This is the case even for the pure model, classical Heisenberg or classical.
for the ferromagnetic one
Yeah, even for
has residual. Oh, okay, I didn't know that. Oh, in the mean field case, you mean?
even in the short range case, I believe.
I'm surprised.
I don't know more also, I know what came from the calculations, but I don't know what happens in the finite dimensions.
Because it's classical. Too long that it's but anyway.
So do you know for the like a short range model, like a Bloom-Keppel model, is there like a Imri-Ma kind of argument which goes through and
Yeah, so in 2 dimensions it
there's
will
no-
go through, depends on, so today I showed the results for the random magnetic field. In that case it will go through. But if the disorder is in the crystal field, no, because it's not aligned to the order parameter of the system. Yeah. Because there are 2 order parameters. Yeah, in this case it will.
it will go
Yeah.
through?
So Shumeda, so this asymmetry change also the when you still have the second order phase transition, the universality class changes or remains, so the exponents.
So you mean to say around these red points? Yeah, so the beta is half. So it is in the Ising universality class,
Okay.
but I'm not sure. I expect if one looks in finite dimensions, like 3 dimensions, the continuous transition in the random field Ising model has a beta which is different than the beta for the Ising model. I expect the beta for this ordered critical point will be the same as the beta for the pure Ising model in that case.
This same.
But
Okay.
those simulations are hard and yeah. So
Okay.
we have not done that, but this is my belief, but I might be wrong.
Okay, thank you.
Yeah.
Any other questions?
So you said there's this conjecture that if the H distribution is a maxima, then you have a second order, and if it's a minima, then it's a first order.
So it is based on the field theory for the Owen models.
Okay.
So this is there in Arani's 1978 paper. I showed the reference on the first
So
page.
it's true even for the short range, or it's for the.
In disorder, there are very few things we know about short range. In 2 dimensions, there are rigorous arguments which says most of the transitions are gone. Most of the calculations are for a long range. And finite dimension simulations, are tricky. Self-averaging is a real problem. And for example, now people say it has been resolved, the debate that in 3 dimensions random field Ising model, whether you take the bimodal or the Gaussian distribution, you should get the same phase diagram. So I don't know if this has been looked so much into the system. Yeah.
And what happens if it's a flat distribution, like it's neither maximum?
So uniform distribution, right? So that we studied in the case of random field XY model, which is like O2 model, right? So otherwise it doesn't make sense to look at the, oh sorry, I went further.
In the Ising case,
So in that case, the distribution was, the phase diagram was like this.
so it's still a first order.
It's still a first order, yeah. I think for ON models that's true, but you know, when there's a spin one, there are these zero sites which is diluting, bringing in some annealed effects. Yeah.
Any other questions? Okay, I had a couple questions. So you said briefly mentioned that when you took a Gaussian distribution instead of these delta peaks, even the first order transitions went away, or what was the?
No, so the Gaussian distribution to start with had no first order transitions.
Okay, I see.
So that is why everything just went away.
Right. Okay.
This was the first one.
Mm-hmm. And,
So it just went away.
Yeah, another question was you can also introduce asymmetry by keeping, by changing, so instead of having H naught and plus H naught, you could have H naught and minus H naught prime.
Yes.
With the same weights.
Yes.
And that also gives similar
Yeah, you know,
results.
the problem is the phase diagrams change so much
Right,
that actually all those are valid questions, and maybe something unexpected can come out also. You know, if H prime by H0 becomes very high, I mean, if the ratio changes, but maybe not in that case. But more interesting is the tri-model or the double Gaussian, you know. So some of those things one is looking at, but yeah, there are many things. Yeah.
Okay, if we have no more questions, let's thank Sumedha again. And our next speaker is Samriddhi Shankar Rai from ICTS.
So, thank you. So, let me begin by sort of wishing RRI a happy 75th. And since I'm the last speaker, I would also sort of, you know, it's not important that I speak for 45 minutes or so. I'd also like to thank, I think on behalf of all of us, Gayatri, Mr. Mahadeva, Mr. Manjunath, who've been sort of incredible in their support for this meeting, as well as all of those behind the scenes who sort of helped us to keep things running. Also, Sanjeev, thanks a lot for the invitation, and in general for sort of keeping the flock together of the community in India, and for being incredibly generous to, especially to younger people like myself. So with that, so I'm a bit of an outsider to, statistical physics in the way sort of that's been the focus of this meeting. So this will be somewhat of a large deviation from the topics that have been discussed. So I'll talk about sort of recent work that have been done in our group, and we are new to this game of low Reynolds number suspensions. We do high Reynolds number turbulence. So whatever I'm going to say will have a strong bias from my own sort of training and the area that I'm interested in. Okay. Some of these figures Chandan, Una showed, but essentially for us, active matter systems will be composed of agents which essentially consume energy and move, right? And they sort of span a large variety of length scales, and what we will look at is at this end of the spectrum. So in this talk, essentially, what we will be discussing is the fate of dense bacterial suspensions. And if you want a sort of physical model in mind, this could either be this variant of a bacteria, the B. subtilis, and the reason is that the early experiments on which much of my this talk is based was done on this system. And also some of it sort of concerns the E. coli bacterium. That's because there's some ongoing experiments that we are doing. I'll sort of just flash them a little, which is on the E. coli bacterium. So what's sort of interesting, so our starting point is this work about 10 years ago by Wensink et al., which sort of looked at this dense Bacillus subtilis suspension, and you have sort of, the details of the bacteria here, and they sort of, looked at the low Reynolds number. So these are suspensions which are at very low Reynolds number, but they flow. And what they saw remarkably was, so this is from their experiments, of the subtilis suspensions, it's quasi 2D. What they were able to construct from the experimental data was what's known as a vorticity image. So you looked at the flow and then you take the curl of it, etc. And then what they noticed was that this is surprisingly close, just pictorially, to what you see in high Reynolds number flows. So this is a snapshot of a two-dimensional turbulence flow. So you can think about a sort of soap film which is agitated and which moves. That's an example of two-dimensional turbulent flow. And there's a sort of remarkable similarity, at least visually, between what you see at essentially flows which are at 0 or close to 0 Reynolds number with flows which are, in the Reynolds sort of going to infinity limit. And all of this, so the fact that, the similarity that you see here gave rise to this sort of whole field of active turbulence, and there are sort of wonderful review articles from which, we learn most of our stuff, including this early work, as well as there's a new review a year or so ago, which is also quite fascinating to actually delve into it. So we begin by sort of trying to ask the question that how does one model such suspensions? So of course, there is the microscopic approach, which is, so goes back to, let's say, the Vixek paper, where you sort of give some rules of the game for individual agents. So you say how the particles would move, how they would interact, and then you try to come up with collective dynamics. So for example, this is from my postdoc Shidato. So for example, you can look at those models and then, give them the sort of interaction rules as you like, and then you can try to understand when they flock and when they show collective behavior or not. So given that, I am from the turbulence background, so this is just not the fundamental pieces of work in this area, but just flashing things that our group has done. So you can, for example, also adapt the Vixek model that I just described to agents which are in a turbulent flow and try to see, what are the relevant scales of particles or agents that you need when even with turbulent mixing, they sort of tend to show these sort of quite interesting collective dynamics. You can play the same game. Again, this is still in turbulence, of course, high Reynolds number turbulence, where you can look at filaments which sort of tend to model various things. So these are sort of very crude models that we had introduced a few years ago, where we try to understand that if you take these filamentary objects, then how do they self-organize? Yes. No, this is really high Reynolds number flows, solutions of Navier-Stokes when the Reynolds number is as high as our clusters. Yeah. So the turbulence is faithful. So the only reason this is not, but the only reason I'm showing is just extending agent-based models, but now the agents are in a complex environment. The only complex environment that I know how to handle a little bit is high Reynolds flow. But this won't be the subject of the talk. I'll come to, I'm just sort of setting the stage, especially for the younger students, and perhaps for advertisement. Okay, so, right. So essentially, and there's this whole list of, so especially the review article by Sriram, etc., were very useful, where you can do more realistic modeling, and I'm not an expert in this, where you sort of make the effective equations more and more realistic. So then you can sort of look at all these sort of classes of particles where you do that. But that's the microscopic approach, which is not something that we will touch. There's a macroscopic approach, and this comes from the following. So this is from some experiments which are ongoing with Shashi's group at NCBS with my postdoc Shidato, where we look at an E. coli suspension, but then we zoom out. And now it starts to look like a fluid, exactly the sort of Wensink picture that you had in mind. And when you sort of look at this as a fluid, then you make the immediate connection, and it's a connection that, we aren't the people to make this, but it has been done in the past, where you sort of take the point of view that you're going to write down a coarse-grained description, an equation for this sort of coarse-grained velocity field that we just saw, which will start to look a lot like the Navier-Stokes equation. And essentially what these people sort of wrote down was the fact that you essentially are able to model these flows. So now this is, it's really at very low Reynolds number. So this is a bacterial suspension. You coarse grain it, and you're able to write down this sort of equation which kind of describes the continuum version of this. So you've sort of zoomed out, and you're not looking at the individual bacterium anymore. And essentially the sort of what we are interested in is what happens when you change alpha. Alpha is the injection rate, so it's sort of is a measure of how active the bacteria is, how much sugar it has, or how much light it has, if it's something light activated. And what one does is then one sort of solves these equations and gets a field which we will sort of look at and see the consequences. So very soon in my talk, I'll probably lose the bacteria altogether, but we'll see how far we can get with that picture. So one of the consequences of actually numerically solving this equation is that as you increase the strength of activity, which is always less than 0, then you get flow patterns which are quite different from one another, which is activity dependent. So in this talk, that's all that we've done in active systems. We'll be asking just the following 2 questions. Maybe the second question I won't touch upon in the talk. But, in what sense are these low Reynolds number flows turbulent? So we'll sort of, take the litmus test of what we understand for high Reynolds number turbulence and see whether the turbulence bit in this active turbulence makes sense or not. And I'll try to sort of tell you a little bit about our difficulties in doing this. Oh, sorry. Yeah, that's good. I forgot to mention.
Is it an individual bacteria or like large-scale velocity?
So it would what would be called the polar velocity of the bacterium. So depending on how much you feed it, so what Julia Yeoman and others did was then to look at typical velocity fields, and there's a sort of lookup table, if you like, where you can correspond your alpha to the physical velocities. I'll come back to that physical velocity and what it means. So, sorry. Yeah. It is in the sort of highly packed regime. So there are 2 approximations that's being made. One is the incompressible approximation.
That's for the fluid, but it looks like you have a lot of fluctuations in the...
Yeah, but when I'm looking at it, I'm just looking at it as a velocity fluid, as an incompressible fluid. So I really don't, I wouldn't care about the density field when solving Navier-Stokes.
So
yes.
you wrote this kind of Navier-Stokes equation. Is that like a fitting equation? I mean, is it phenomenological?
It's phenomenological.
So you try to see in what sense you reproduce the pictures.
Exactly. And so again, I would sort of strongly recommend the PNS 2012 paper where the best part is the supplementary information where they go through these fittings very carefully. I mean, we can talk about that after the lecture. Yes. So, yeah. In our experiments, they sort of, it's dense, and we make measurements for a few minutes. So this is something, it's just very short. I'll come a little bit if I have time to look at the experimental data, which for me is just a guide right now. I mean, I don't think I have, slides with data from there. So anyway, so what I should like to highlight is that these questions were really answered by Shidatta, who's a postdoc. He's now on his way to join as a faculty member at IIT Kanpur. Rahul, who was a PhD, so Rahul and Martin were students, so Rahul is now doing a postdoc at OIST, and Martin is still in sort of, living systems group with Agnese Seminara in Genoa. Okay. So let's start. So this sort of, this talk will be based on this sort of recent work of ours, which I will. Okay, so before that, since I asked in what sense are the flow turbulent, so now I'm slightly more in my comfort zone. So let me flash a couple of slides to say what I mean by fully developed turbulence, or what is the yardstick on which I'm going to base. So as we know, turbulent flows are commonplace. So this is high Reynolds number turbulence. and fully developed turbulence. So if I want to quickly flash what are its sort of salient fingerprints. So these are, of course, flows at large Reynolds number. They are in a non-equilibrium steady state where the energy injected on average is balanced by what's dissipated. So the telltale signatures, at least for me, is the fact that they are chaotic, that they're irreversible, of course, that they're intermittent, and sort of Chandan spoke about intermittency, and essentially what you can look at is this sort of spiky behavior. For example, this is energy versus time, or this is the dissipation rate measured in a wind tunnel versus time, sorry, Sanjeev, where you have this sort of spiky behavior. So there are periods which are on and periods which are off. Or you also see it, this is from Antonio's sort of work several years ago, where you look at the mixing of a scalar field and you see these sort of sharp fronts. So there are regions where things, whatever you're measuring, are high, and where things you measure low. And of course, they have multiple length and time scales. So essentially, what does it mean to be turbulent? So if you're looking at inertial turbulence, high Reynolds number, then what we know is that there is a certain universality of scale invariance. So this is a bunch of data from numerical simulations, experiments, observations, where you, I'll define this more carefully in a minute, where you measure the energy spectrum, the distribution of kinetic energy across Fourier modes. And we know since the work of Kolmogorov and later sort of refined by Frisch and Parisi, that there are these intermediate scales where it doesn't matter where you're measuring, you always end up with a power law, which is k minus 5/3. So there is a certain universality. And the other sort of interesting thing, which is what I mentioned already, intermittency, is that whatever you measure, and this is a measurement of the velocity gradient, you would end up with these sort of fat tails or large tails, and they sort of, they sort of keep getting fatter and fatter, if you like, as you keep on increasing Reynolds number. So what early studies, and these are two very nice papers, so this is from Bratanov, Yenka, and Frey, what they showed was when they measured the energy spectrum, they found that it is a non-universal, it has a non-universal behavior, and although you do see some scale invariance, the exponent actually changes with different values of alpha. So these two from their work are for different values of activity. So you change, let's say, the sugar concentration in your suspension, or you shine light with different intensities for bacteria which react to light, and then and then they end up showing a different power law. And the second thing, this was from Wensing's work, so you see there's a lot of data which collapses together, and what they found, and they sort of commented on this, that although this is active turbulence because they're vortical structures, when you actually measure the analog of the velocity gradients, you get a beautiful sort of Gaussian without any of these large tails. So such studies suggest that bacterial suspensions are not really turbulent if I'm sort of if I'm sort of trying to make this very strict yardstick on which turbulence is measured. So in a nutshell, what we showed in this paper a few months ago was that, and I'll go through this result, was that there is an approximate scale invariance which emerges with a universal scaling exponent beyond a critical activity. All right? So let me go through this kind of slowly. So what one does is, both these measurements are essentially measuring the energy spectrum, which is just the energy in Fourier modes, and you make an ansatz that this is k to the power delta, where delta is minus 5/3 in high Reynolds number turbulence, independent of the mechanism, independent of where you measure. As long as your Reynolds number is large enough to detect a power law, you will get minus 5/3 modulo some correction. So what we then do is we take our equation, and then, and this is the bias which comes in from high Reynolds number turbulence, then we do what is known as a closure approximation, which people used in the 70s. It goes back to the work of Kreikner and others. And what one does is sort of closes this equation at the second order. So you sort of make certain approximations and sort of replace the 4-point correlator with sums of 2-point correlators and assume that what you leave out is not too bad. And essentially, to cut a long story short, you end up getting an equation for the energy spectrum, which has this flux, which by definition is the amount of energy going from scale to scale. All right. So what we do then is to make the following ansatz, that there is an effective time scale in the problem. We do not know what that is, so it's some k to the power xi. We plug that back into this equation. So after this, the algebra is reasonably straightforward. And then we get, of course, you put this in here, you essentially get a formulae for the energy flux. And then you can sort of go ahead and then solve this equation. So what we do is at low activity, and I'll define what low is in a minute, but just to give you a sense of where we are headed, at low activity, the assumption is that the effective time scale is going to be constant. All right? So why do we assume that? What we assume is, if you remember from the Bratinov, and I'll show you, if you remember the Bratinov result where the energy spectrum is k to the power something positive, so it means that the large scales are not energetic. So one assumes that there is no driving, unlike real turbulence, coming from the large scale, and then you can go ahead and actually solve this equation with this ansatz, and then you get back the old result where the energy spectrum has a scaling exponent delta, but then delta depends on alpha, on the degree of activity, unlike now, real turbulence. Yes, sure. This is for the range of k where we are expecting to see some scale invariance, because that's when we are defining the fluxes. So this is not for the scales where. So the reason I'm struggling with it is I do not know whether I should use it for this suspension, but in high Reynolds number flow, this would be in what's known as the inertial range, where you have a certain flux of energy going from scale to scale.
So in this active case now, the flow of energy direction has changed compared to inertial. That's why you get a decay in the.
Well, that really doesn't give you the direction. What you need to look at is the sign of the flux to see where the energy transfer is happening.
And on that energy flow, where does the persistence length scale comes in? So when you had the energy cascade plot?
Yeah, it wasn't an energy cascade plot. This was just a plot of the spectrum. So this doesn't tell you the direction in which the energy flows. For that, you have to look at the flux. So you have to look at the net energy going from the left modes to from the lower modes to the higher modes, or the higher modes to the lower modes. I'll come to the flux in a second. But this is just the energy spectrum. So this does not by itself tell you the direction of energy, flux. Okay? So for that, you need to look at the sign of the flux, which I'll come to. So to answer you quickly before I get to the slide, there's an inverse flux of energy, which is again consistent with 2D inertial turbulence. Okay. So that's the ansatz, and with that one can actually solve this equation and find an exponent which is activity dependent. Yes, Kapita?
What is this k to the power z? The delta has tau effective, and tau effective is k to the power.
So this is an assumption that we've made.
So ek is going with k to the power z, is that right?
No, ek is going as k to the power delta.
But
Delta is the spectral exponent that I'm after. Sorry.
next slide.
Yeah.
Delta is
Delta is the exponent sitting here.
no in the red.
So the value of delta is this.
Is tau effective by lambda. Tau effective is k to the power z.
That's right. Where xi is 0 here, so it doesn't matter.
Well, I think Kapita is asking that delta is a constant integer of k, but on the right-hand side you have tau is equal to side.
But when xi is equal to 0, it's k independent. Okay, I wrote this. Actually, thank you. Now I understand. So there is no k dependence there, because this is in the regime where we've assumed delta xi is equal to 0. So this is really a constant. There is no k dependence here. Does that answer your question, Kapita?
It's only for z equal to 0.
Yeah. This is for xi equal to 0.
But you don't know how effective it is.
No, we'll come to that in a second. Yes. So this is just an ansatz, and then we are going to. So for us, we always have to go back to either the experiment or the numerical data to check whether the ansatz are. Of course, in reality, we first look at the data and then come up with the ansatz. But okay, Kavita, that's it. Yeah. Okay. So then and so this again I'm showing from Bratinov's paper. Then where they had looked at this tau effective, they find that the tau effective is sort of flat in the scales where we are trying to calculate the spectral scaling. So that's sort of consistent with the ansatz of xi equal to 0. All right. So now what happens? So the question is, how low is low when I mention low activity? So again, here I go back to the bias of high Reynolds turbulence. So what you see from this exponent is that as alpha starts to get more and more negative, or the suspension becomes more and more active, at some point, delta will be order 0, right? What that would mean is that the large scales are also going to be energetic. And so in principle, they can drive, like in turbulence, real turbulence, flows at the low scales. So what we sort of claim is that there is an alpha C, which you can fish out from this, when delta goes to 0. So you set delta equal to 0 here, and that gives you a measure of alpha C, which turns out to be of the order of -5. And there, certainly, this constraint doesn't hold anymore, all right? So now we again go back to the equation that we have. That's the equation that we are going to solve analytically, and this is all that we sort of get from our different hints. And when we do that, we sort of claim that there could be what's known as a local turnover time scale. That's the standard game we play when we derive Kolmogorov's k minus 5/3 result, so that there could be sort of 2 time scales in the problem. One, a local time scale, which is a la Kolmogorov, which is this dimensionally turns out to be a time scale. And then there is a sort of 1 over k, and this again comes from insights from the experiments in numerics, that there's going to be a 1 over k, and then you can construct an effective time scale from all of this, which includes the delta now, all right? And that gives you the flux, which is, just from this formula. So we can actually then go ahead and measure in our systems what the scaling of those tau effective, and you remember this was flat in the Bratunov work, which was for mild activity, and then you see that there's sort of beautiful scaling emerges, and essentially what one finds is that the tau effective is essentially k minus 7/8. The flux is k3/8, the question that you were asking, but this is inverse, so there should be a mod here really, and which gives rise to an energy spectrum which is k minus 3/2. So no alpha dependence in the spectral exponent anymore, as long as the minute alpha crosses, well, roughly alpha crosses alpha C, all right? So to summarize what we sort of, what the closure model a la Crichton, etc., tells us is that one is able to fish out this delta, the exponent of the energy, the scaling exponent, and one finds that there's a transition from an, okay, now there's no tau effective, so, okay, good. So what one sees is that there is an alpha dependent scaling exponent, and then when alpha crosses the alpha C, it becomes very active, then it sort of sticks to a universal exponent, much like real turbulence of -3/2. So here's a plot, for example, of things that we measure from our simulations. And so essentially the sort of punchline is that these bacterial flows tend to be beyond this critical activity much more like real turbulence than below. There is one sort of embarrassing bit that one needs to point out, that the transition happens really at around -5. Our theoretical calculation suggested it will happen at around -10. We looked for a factor of 2 for a long time. We didn't find it, and so we stated in the paper that probably 5 and 10 at this level of approximation is perhaps, okay, a forgivable sort of offense. Okay, so this was sort of, so then we sort of also look at, are there evidences from other works which sort of suggest that this transition might happen? So there's this sort of recent paper on Voigt's group, I mean, it appeared on Archive a week or so ago, where they look at the same sort of transition. This is a measure of the activity. They measure the spectrum, and they see that it indeed goes and then sticks to. Well, they say it's k minus 5/3, but the whole literature is riddled with these k minus 5/3 because of the Kolmogorov bias, I suppose. Shiddatto painstakingly digitized these data and found that -3/2 is just as good. I mean, you really can't tell, except that, we have some reason to believe -3/2 just from theoretical reasons. Then there are these sort of experiments on different systems, which also ballpark show that once you reach high activity, you get this transition. So to answer Shanton's question, for example, the activity where we sort of suggest that there is a transition to universality is an activity which has typical speeds of 70 microns per second of the bacteria. And that's experimentally realizable. I'll show you examples of that in the last sort of 10 minutes that I have. I'll comment. So hopefully, this alpha minus 5, etc., is not outrageous when it comes to real systems.
Is the idea that one has an effective Reynolds number?
If you calculate the Reynolds number, is effectively 0. So.
Yeah, but an effective one somehow, which is related to the bacteria flow themselves.
Yeah, I mean, we haven't really explored that line because the way certainly people like us in iReynolds think about Reynolds, here we don't really find a reason that with increasing alpha that you suddenly sort of cross over to something which is moderately large or even finite. So again, I mean, it's not something that we've explored, I mean, just because, I guess, of our biases. Yes, Chatta. Yes, so we are actually doing it. I mean, when I do it, it's not very well, but when Siddhartha does it, it somehow works. So there are two ways. So first, we were trying to look for these bacterian strains which get activated by light. And we tried asking friends if they could give us some. So there, the intensity of the light, and I'll come to the end where we are doing some new work which is in that line, where you can sort of change the activity. The easier way that we've sort of discovered in Shashi's lab at NCBS is, I forget the exact composition of the sugar, but essentially if you feed them, if you make them high with a lot of sugar, they tend to move faster. So there is a way in which we can control activity, and that's something Gil, Ariel, and other groups in Israel have played with in the experiment. In the experiment, so the experimental result so far is this. This is in the group of Tirumala, where they looked at some epithelial cells which they tried to make active. So they actually reported a range of exponents which were from minus 1.4 to minus 1.58 or something. So we were quite happy with that, yeah. But there's something else where I'll show you a confirmation, real confirmation experimentally about this transition, so from a different point of view. The spectrum, I should tell you, I mean, I think I had a caveat somewhere that it's still to be completely confirmed experimentally. Okay, so this critical activity also, you remember I told you that it's also not intermittent, which is another signature of real turbulence. So now that we had this picture, we went ahead and looked. So by the way, these alphas were all in that range in the earlier studies. We actually looked at, so this is a visual illustration of what intermittency really means. So we take a snapshot of the vorticity field, and we filter it for values which are twice omega RMS, 4 times omega RMS, 6 times omega RMS, basically sampling the tails. And at low activity, which is this, by the time we come to 6 omega RMS, you see no red or blue speck. So there's nothing. It's exactly what Julia and others reported. But when you cross alpha C, so this is beyond alpha critical, then when you play this game, you see that there is a form of intermittency, which we are then able to quantify, let me not get into this, through kurtosis and the different measures that people use to actually understand scale-dependent intermittency in these problems. So finally, we sort of use this idea that Shubro, Abhishek, Anupam, etc. introduced on this many-body chaos, and Manas sort of mentioned it yesterday as did Sriram. So what we also sort of looked at is the fact that the results are not that critical. I want to get to the experiments, and I'm running out of time. But essentially, what we looked at is what is the chaotic nature of these suspensions. Why are we looking at this? That's because in turbulence, there's a very beautiful and fundamental result that chaos is unbounded to the extent that the Lyapunov exponent that you measure is a function of the Reynolds number. So the mean field calculation gives you a square root Reynolds, but there are corrections which others have found out using multifractality, etc. But the point is it never saturates it. So you buy a bigger wind tunnel, you get a larger Lyapunov exponent, or you buy a bigger cluster. What we find, and this is really the Lyapunov result that I want you to keep in mind, is that, and there's probably, Christian, there's only one comment on this in answer to your question, is that the Lyapunov exponent actually increases when it gets to the critical activity, it kind of saturates. So the maximally chaotic states sort of emerge at that critical activity. So do you have 5 minutes, Shubhan? Yes. Okay. So now we can, with all of these ideas in place, we can then start to ask the question that what does it mean for mixing, which presumably may have something to do with why the poor bacteria might be happy that these states exist. I don't know the last bit, but let's look at what happens to mixing beyond this critical activity. So now what we do is we play, again, Chandan sort of discussed this in his tracer thing. What we do is we seed these flows, so these are at different activities. We seed these flows with Lagrangian or tracer particles, and we just want to follow what happens. And this is something, Chatu, that people have reported in experiments over many years, starting with the early work of Lipshaber, et cetera, right? So we sort of, and this is from a slightly older paper that you have the reference there. So what we find is that when alpha is, remember alpha critical was about -5. So when alpha is, -1, -2, -3, -4, these trajectories all look diffusive. So this is sort of, take real trajectories from our simulations just for visualization, and Shiddat is fantastic at this. He sort of put them into one origin just to make comparisons, and then you see sort of this sort of diffusive trajectory. However, when alpha becomes -6, or beyond the critical activity, what you find is that in an ensemble of of tracers, you find distinct trajectories. There are some which have this sort of persistent and straight trajectories, and then there are some which are just meandering. All right? So this is the fact that it's sort of uniformly lit up. So this is, what I will not discuss is how it's related to the flow geometry, because that becomes too much of fluid stuff. But just to summarize, that there are in the emergent flows, there are distinct regions in the flow, and depending on where your trajectories begin or spend most of their time, you get these distinct sort of 3 kind of trajectories. So what does all of that mean? So I'll just give you one result and not the others. So what it means is that one can now sort of try and understand what happens to the standard measure of mean squared displacement. And we sort of looked at it for the different cases, and we asked the question that, at long times, whether this is t to the power psi. So why do we ask this? So this is our result. So this is for very low activity. And we find that, you have the simple sort of ballistic to diffusive transition, which is consistent with, for example, this is a result from the IIT Madras group, where they had seen this transition. However, what we find is that when you actually crank up activity beyond that alpha c, if you sort of follow the numbers, when it gets beyond alpha c, it goes into a super diffusive behavior. So everything becomes t4/3 from t. And this was very nice. That's because there was a slightly earlier work. There were actually a lot of work on this mean squared displacement in bacterial suspensions, largely experimental. So I'm just picking out one because that's the one which sort of agrees best with, but I'll flash the others which don't. No, so the only thing that we sort of tried to do it was the Levy statistics, just to find that it's sort of, you bootstrap ourselves and see that things are. So this connecting with the minus 3 halves, there's no sort of, at least none that I can tell. And so this was a nice bunch of experiments by Gill and others, where they actually found that the mean squared displacement in their suspensions are, 1.51. I mean, this t4/3 is, the value 4/3 is not something I'm sold to. I mean, the only point I'm trying to make is that there's a transition to a super diffusive behavior. It could be, I mean, numerically we found 1.3 something, so 4/3 is easy for us to, so in the paper I give the number and not 4/3, okay? It's a shorthand for something which is 1.3, whatever. And then more recently, this is a group from IIT Kanpur. They also report in this archive preprint, again, mean squared displacement, which is where they get a transition. As you were saying, they could tune the activity by shining different intensities of light, and they find this transition from simple diffusion to super diffusion. So this is, as all of you know better than me, this can be, so one looked at whether there is evidence of Levy walks and the anomalous diffusion being an outcome of that, and we, one could measure all of that and see that this is self-consistent with Levy statistics. And these are sort of more experimental results which sort of confirm the distribution and the exponents that we obtain in theory. High Reynolds number is diffusive. So yeah, so I'll make that remark in a second. Okay, so it's already there. So that's why I end the talk with the sort of statement I began with. So what we sort of, so the things in green are things I talked about, but what we sort of showed, this was very interesting, that there is now some experiments which sort of send us their early results where they sort of see, so what we claim is that all the sort of mixing process is mediated by an emergent sort of new structure in the flow, which we call streaks. So it's, if you want to imagine, it's a bit like the laning phenomena that people observe with other sort of soft matter systems, but it's not exactly that. And so we sort of claim that there are these novel streaks which emerge in the flow, and there are sort of signatures of dynamical heterogeneity in trajectories, which you could guess from the earlier picture that I showed, that just like in sort of very loosely speaking in glassy systems, the same sort of dynamical heterogeneity you see. Where are we now? I mean, we are more or less done with, I think, active turbulence, but there's this very young student, Kunal, at ICTS. He's sort of asking the following questions. I mean, the one in blue, actually, the others we are still sort of looking at from our old stuff. So essentially what he's asking is what happens if there is spatially varying activity? So it's something that apparently in experiments one can do. Our interest was whether one can sort of, this setup is just the flow, so it's very low activity outside and it's highly active inside. Our point was, seeing what we did with the statistics of trajectories, can we use them to actually localize trajectories in this suspensions? And he's been looking at that, and recently, and I'll end with this really, and recently, in the last couple of days for this meeting, what we sort of started to worry about is what if the activity is spreading? And the reason we worry about it is, again, it comes from some insights in experiments where you do see that the more active guys can actually start moving and, making other places agitated which were not. So we are sort of coupling our sort of model with just a simple advection model for activity. So you begin with a banded structure, low activity on both edges. In the middle, things are very active, so there's a lot of sugar or whatever. And then you want to see what this means for mixing. This really is motivated from certain questions in high Reynolds number turbulence, which has to do with entrainment and active scalars. I mean, Mustances have worked on these active scalar models a lot. So I've sort of looked at the passive problem many years ago with Rahul. Because we have a little handle on some of the theoretical tools here, we are sort of using this as a surrogate for an active scalar problems. As I said, we've sort of moved a little beyond the bacteria that I began with, and so hopefully we'll have something interesting to say about what happens to these fronts of moving activity. Okay, with that, I'll end. Thank you.
Hey, thanks, Samriddhi, for a very colorful talk. Do we have time for questions?
So, is it possible that, like, for example, if you take a large system, eventually it is diffusive, but this for ballistic to diffusive happens in a large crossover region, and
yes.
that you see some exponent basically between 2 and 1?
Yes. I don't agree that it will, but okay, so what's the statement? The statement is if I took that curve of MSD for even longer times, which we did, eventually it turns diffusive, T. What I do not kind of agree, which was the earlier year, is that it's a crossover. I think it's a real regime because it's sort of robust up to a long time, and this time when you sort of see the crossover to T, that's something which we didn't discuss, that's something I can tune with my activity.
And do you understand this crossover time in terms of some physical time scale in your system?
No, we didn't for a couple of years. So the earlier work of Ashwin Joy and others and several people looked at it, where they sort of looked at this crossover from T squared to T And that time scale they were able to predict from some combination of parameters in the problem.
Yes.
So I think it's roughly in that same ballpark. So
So I think the first one is probably easy to understand, but then like
the
you
long
have-
time
you have-
up to
you-
when it persists is
because you have
something
two
other.
time scale now, right? The
Exactly.
next other time scale you don't have.
For the long time, that might be the year, but that's not something that we had looked at. But I know that there are calculations that where you get it from the combination of gamma zeros and gamma ones.
I mean, since this is 2D, can one also discuss here the entropy cascade?
The 2D entropy cascade. So in 2D inertial turbulence, the entropy cascade is a consequence of the second invariant. In this model, we have actually tried to look at it. It's
Because the pictures, suggest that the vorticities have, I mean, that's what brings us to thinking about chaos, right?
Yes, but then in 2D, the reason you're thinking of both the direct and indirect cascade, if I sort of put it in that language, is because there's a certain scale separation which emerges, which is a function of the Reynolds. Here, I'm not sure. I mean, we haven't looked at it. The spectral measurement, and this is not rigorous, but just from experience of looking at these in 2D, the real Navier-Stokes, seem to suggest that there's probably just the inverse cascade of kinetic energy.
And not
Yeah, I mean, partly because the scale of injection is quite large in these systems.
What is the scale of it? You mean the activities?
Yeah. So essentially, my feeling is, and this sort of, Rahul Singh, and I did sort of play with it a little, just to artificially kind of make the scale separation to see if the entropy cascade that you say emerges. But so far we haven't really pushed too far, and neither did we get anything interesting when we started playing with it.
So this is normally, if you think if the bacteria is more active, it should drive the fluid, right? But here in your equation, it appears as a damping term. Like, what is the physically? How do you?
No.
Why is, like in the equation, you have like alpha plus beta used.
Yeah, alpha is the activity which has a minus sign. So the more minus you are, the more it's driving.
But
so
minus alpha u, right? So it looks like a damping of the velocity.
No, but alpha is now minus.
Alpha is negative.
Oh, so it's just a historical convention from Wensing and everything. Yeah, I keep getting confused, but I didn't want to change the convention that you have.
It's positive.
Yeah, beta is positive. So that just comes from the Toner 2 equation of the free energy functional, which Toner 2, Striam, etc. worked out many years ago. Yeah, this is, I mean, at some point I should probably highlight this a little bit more carefully.
Just about the length scale, I was wondering that you have in active turbulence that some increasing part and then falling off. Increasing part is a like power law that you
The
mentioned,
spectrum,
which
yes.
is like non-universal, like
And then
in
becomes
general.
universal.
Then it becomes to universal.
Yes.
No, I was wondering that when this, I'm just trying to understand that when this crossover is happening from increasing to decreasing region, what that k, what length scale that k corresponds
okay, so there are two ways to think about it. In experiments, you think about it as the length scale of the bacterium, roughly. In the model, you can construct that, so that's the unstable mode that you can construct from the parameters gamma 0 over gamma. I mean, I don't exactly remember the formula, but we can go to the blackboard and work it out. So, so that comes from that unstable mode.
I see.
That's the injection. Okay. So that's again related to his question about whether we can get the.
Yeah.
We tried to kind of artificially sort of some scales beyond that.
But experimentally, you are telling that that is the bacterial
Yeah,
length scale.
experimentally, people have seen that scale quite. So that's the sort of fitting, as someone was asking, that was done and verified some 10 years ago in the first papers, where they looked at both particle simulations, hydrodynamics, and experiments and put it all together. And also to decide, why alpha minus 6 corresponds to 75 microns per second. So actually, this sort of this super diffusive behavior, Shanta, was actually seen in some experiments before, even previous ones. Some said diffusive, some said super diffusive. They all had different velocity scales. So, Rahul and Siddhartha went back and sort of matched what they correspond to our alpha, just to be sure that why there is this confusion about it.
Okay.
I still was wondering about this picture. The spreading of activity, is that via the fluid that it goes?
So in this case, there is really no spreading. That's because alpha is frozen. What we did, okay, I'll tell you why we did this. So what we did was we fixed a value of alpha here to begin with, which was, -5 or whatever. And then there was something much less active
There was
outside.
also pictures with the band structure.
Yeah, this is the one where
There.
alpha is being advected by the fluid. So this is just an
by
advection.
hand, by hand.
By hand. So this is just a toy model we are looking
So
at.
it's not that the activity kind of spreads through the fluid to excite the other bacteria. I mean, leaving not by hand, but you just start with active.
We
bacteria.
start with something active, and then we say that that activity is advected by the underlying fluid, which comes from
you
the other
put that
equation.
in.
So yeah. So
But
it's
that would not happen naturally.
no, if I don't have this, there is nothing here which dictates how alpha will spread.
Via the fluid, I mean, I can.
Yeah, but for that I need another set of equation.
Okay, on this in the simulations, but
Yes.
if you would model the fluid in the simulation, that
Then it would spread, but that would be in this class of wet active matters where so here I've sort of, what in an experiment would be the motility buffer, I've sort of integrated that out, so if you're careful, you'll see that this doesn't conserve momentum. I've sort of assumed that momentum has been carried away because of the finite lambda, etc. I mean, non-unity lambda and all of that. So for a wet system, you would have exactly what you're saying. So presumably in the experiments that we are doing, there is some sort of spreading. So there what we are doing is trying to add little polymer pieces because we know in high Reynolds what the effect of that is to see whether there's a coil stretch behavior which is mediated by the bacteria. Sorry, Yogesh.
So this Levy walk, you said that's for the tracer particles,
Yeah.
right? So the bacteria themselves, they don't move much, is that right?
Simple, yeah.
Or they're
They're
just
simple,
kind of...
all the, run and tumble.
So
all
these
that.
pictures are all tracer particles.
No, this is the coarse grain vorticity field. There are no particles here. So
no,
this
if you
is,
put tracer particles, they would roughly...
yeah. So because they're just falling equal to you. So this is just a curl of the U field that I'm getting from a Navier-Stokes-like description. Yeah, so there's a lot of cheating involved, of course, and part of it is what Christian referred to in terms of sort of decoupling from the medium where the bacteria lives.
Just a quick question. So here,
Yeah.
can one tune the dimensionality of these systems in experiments? And do you reckon the exponents will depend on the dimension?
Okay, so about the exponent depending on the dimension, I do. In the closure calculation, the dimension appears more subtly. All right, so one should, it depends on how you define flux, which in itself might depend on dimension. In the experiment, what we've done is we've sort of looked at various geometries. So one, we looked at a wedge geometry, where we put the suspension just to see how the boundary effects play a role. So typically, we are still looking at quasi 2D. So the thickness is maybe just a couple or 3 bacterial lengths. What is really not known and something that, actually I'm not sure that I will continue working on this sort of active things, is that in 3D, in the bulk, what happens? So all the recent reviews sort of comment on this, because for us, it's, in an experiment, so in Shashi's lab, we looked at droplets of these suspensions. So that's really 3D. And then sort of the microscopy was up to some depth but then again, I'm looking at cross sections. And we know from high Reynolds number, that's not a very useful way to look at it. If you look at high Reynolds number turbulence and you take a cross section, optical cross section, you lose many things, including the essential notion of incompressibility. Your 2D cross section will no longer be incompressible. So in our simulations, we already have, but we sort of kept the gunpowder dry because we are still looking for some experimental results to come so that we know, because there's a lot of, because I don't know the field, I'm new to the field, so there's a lot of things that I would rather wait for the experiments just to see and find my way in 3D. But in principle, the 3D theory is not.
Yeah. Do you have any more questions? Okay, so if you have more questions, you can ask him later. So this brings us to the end of the conference, and thank you all for participating. I'll hand over to Sanjeev.
I guess I should say something. Okay, so this is the end of all the talks, basically. So yeah, thank you all again for coming from various places, and I hope you enjoyed your stay here. I should also thank the RRI administration, because I mean they are actually fantastic, and they managed to get us a very generous funding, which help us to organize this conference without any headache. Because as you know that like organizing conference, getting the fund is one of the major thing, and I didn't have to do anything because they just gave us this pot of money and they said, okay, you just organize. So apart from that, of course, I had a fantastic help team. I think they should be probably somewhere here. You have already, Manju, can you come? Yes, okay, yeah. So I think you have been anyway meeting them, but okay, Manju has been really very helpful, and Mahadeva is like this thing. Then Gayatri has been very helpful for this thing, and so of course we have this purchase department and account, and then finally all your transportation has been basically taken care of by Manjunath. And there was one more person, Sachin, but okay, he had to go to CNR's birthday, so we are missing him here. So, I mean, so it's great to actually organize things at RRI because of all these fantastic people, and like they basically help us a lot, actually. Yeah. And I think I was supposed to say something else, but I have just forgot. Yeah. Yeah, okay. Yeah. Yeah. And of course, we still have, okay, so the lunch is at 12:30. It's starting at 12:30 today because we don't have anything else. Okay, we still have tea, I think, downstairs. And yeah, okay, I think Supriya has something. So maybe I'll just give it to Manju. Okay. So this is for all, but I'll probably just hand over to Manju, and this is from Supriya all the way from Sweden. Yeah, okay. Yeah, thank you very much, and probably again see you in RRI, no, downstairs, but probably in a couple of years again in RRI. Like, okay, it's a very nice group we had here. Thank you very much. Yeah.